All right, so this video is just going to be something interesting that I found out at work the other day. Basically, this is a solution I had to come up with for a unique set of problems, and I figured I'd toss into a video for anyone else who's run into this exact same kind of use case for this scenario. So the scenario I want to make this video about is constrained regression. So what I mean by that is linear regression, but we're using it in a way that we want the coefficients on the variables to be constrained in some way. So the use case in my particular example, without getting too much into the details of what I do and all that stuff that might be a little more sensitive, the premise was that we were basically coming up with a pricing model that was very much mimicking regression. And I say mimicking because we weren't using it necessarily to predict as much as to fit as closely as possible a previous pricing model. And we were basically boiling it down to some fewer variables to apply fees to. But a really important part about this is that some of these fees needed to be at least above zero. So you don't want to have to give some franchise owner or any type of customer a fee on some negative value, even though using pure regression could, give you this scenario. So we definitely wanted to keep it above zero, and using just regression worked fine for that because you can kind of snake your way through and say, well, if you get a negative coefficient, just run it without it, and you can just kind of use backdoor methods that way, and that tended to work pretty well. But the other thing that we ended up wanting is we wanted some fees to be more impactful than others, and it didn't matter if they negatively affected our fit to the previous costs, because there's a lot of business value in having these fees be correctly aligned with what the business needed. So in this case, we were thinking about doing it manually, and I have an optimization background, so I started sort of researching ways that we could just look into, regression and maybe think about it from a different way. And what I kind of realized is that, regression, just like every machine learning algorithm or predictive algorithm, however you want to call it, is ultimately an optimization problem. And at the heart of regression is usually, there's plenty of different kinds of regression, ridge regression, there's Bayesian regression. But your standard out-of-the-box regression is going to use something called least squares as its cost function. And then it uses gradient descent, which is an unconstrained optimization problem, to find the optimal solution. So the least squares is just the minimal amount of space between your cost function or your target variable and whatever you're trying to predict it with. So how you find that distance is you do basically the square root of the Euclidean distance, so x minus b, squared, and the square root of that, which basically puts it into a general umbrella category of quadratic optimization problems. So if we're thinking about it just from an optimization standpoint, well, there are quadratic programming optimization problems out there that do have constraints. So I kind of figured there was probably a way to apply constraints to a least squares problem. And in fact, there is, and it's nicely built into SciPy, which is why I'm using Python here. So in this short video, I'm just going to go through how you could apply this sort of constrained regression. And I know that's not technically what it is, but I think that's how it would be useful to most people, and how you can implement this in Python, and hopefully it'll be useful for you as well. So I'm just going to start by bringing in my standard libraries, NumPy and Pandas for bringing in data, and NumPy really for putting in the parameters of this optimization problem. Now I'm using SciPy optimize, and I guess I only want to bring in a little piece of that whole package. So and we are going to import linear least squares, so it's called LSQ linear. I believe. Let's see if that runs. Oh. Okay, so that seemed to have run. So we're using the SciPy package, and we're using, instead of a linear regression, we're using LSQ linear, which is a linear least squares. And now I'm going to use an example. I've got some dummy data from Kaggle, and I'm just going to use this housing data to say, if you are going to build the exact same kind of constrained regression that I did at my work, how would you do it? And could you do it with, could you do it to actually really mimic regression? And so we'll find that out. Okay, so the first thing I'm going to do is read in my data. So like I said, this is housing data, so I'm going to I'll just call it DF. That's usually the easiest way to go about it. I'm going to use the pandas read CSV function. Go to my data sets repository. And go ahead and read that in. And just go ahead and take a glimpse at it. And there's quite a few rows. So it's so big that the Python notebook doesn't want to display all the rows all at once. So I'm going to go ahead and just print out the name of all the columns. And you can see there's quite a bit there. So in my imaginary scenario, and if you're following along for your own purposes, we're gonna try and predict the sales price as closely as possible. But let's imagine in this scenario that we're an international real estate firm, and we want the most basic of models just to use as a base, as a benchmark to, let's say, test some of our assumptions worldwide, like just to kind of test that there's nothing screwy in any of our other systems that may be using more sophisticated methods to predict prices. So this is just really to give a really good benchmark, but we definitely want all the variables to be above zero. We want this to be something you could do by hand if necessary, and something fairly intuitive. So something like, $10,000 for every bedroom, or something nice and sort of simple like that. So with that in mind, let's try and pick a handful of variables from this data set. So reading through these different variables here, let's see here. Lot area, I think, makes a lot of sense. I think if you're going to buy a house, the size of the lot absolutely is going to be a main factor. And obviously going through here one by one and picking them is not ideal. We could use R squared, or we could just simply use a cost function and try variations of these variables to see what is the most explanatory. But for this purposes of this model, I'm just going to talk through it, and we'll use the most logical variables we can think of. So lot area makes a lot of sense. Secondly, I think there's one I saw above here. Yeah, not basement square footage. Well, while my eyes are searching for that, I'm also going to say garage cars. How many I think cars you can fit in your garage, I think is probably pretty predictive. It's probably a pretty nice thing that people can really understand and think about. And it's probably has a pretty substantial impact on the price. So I'm going to include that as well. And for a third one, I think there's going to be something here that basically represents, here it is, GR live area. This is a ground floor live area, or anything above the basement. And this is basically the area, the square footage of the house above the actual ground. So I'm going to make those my predictive variables. And to do that, I'm going to kind of subset this and then turn it into a NumPy array. Because as I use this LSQ linear function, I'm going to want to feed it NumPy arrays as values. So I'm going to call this my pred map, or predictive matrix. And these are just going to be my independent variables. And I'm going to use it, the df and I'm going to subset it with my columns, make it a vector of columns, lot area, this one always escapes me there, gr live area, and then we'll do garage cars. And we want this to go into NumPy. So we're going to go ahead and say as matrix. All right. So we'll just take a look at that real quick, see what that looks like. And that is a standard NumPy array with 3 columns, lot area followed by the above ground area, and then with the number of cars in each garage. So another thing we're going to need is we're going to need our predictive variable, and I'm going to call that pred var as our kind of target variable, and that's going to be sale price. So pretty simple. We'll just make that into a NumPy array. Great. So we should be ready to run our function, right? No, of course not. So this is still not quite mimicking our regression if we wanted to do that. So one of the beauties of a regression is it has that bias coefficient, which does not attach to any variable. It's just a fixed value. And when you think about a cost, it's actually pretty nice to have some sort of base fixed value that you can just start off the ground, you know, as an assumed cost. So in this case, we're going to tack a column of ones onto the predictive matrix to make basically our variables exactly as linear regression would have them. So in this case, I'm going to first just make a column of ones. I'm going to go by the shape of the pred map, and shape's a 2-dimensional variable, so we'll see if that works. Nope. I'll call this nums array. Oh, it should be np.ones, right? And probably np.shape. There we go. Coming from R, it's a little dicey to remember all the time to those names in front for the packages. So I can't spell today. That's not very helpful. All right, great. So now we have this array of ones that I made with the np.ones function. And now I'll go ahead and concatenate these guys together. I'm just going to rename my variable np.concat innate. I think that's right. Oh, and see how this is kind of a sideways. It's row wise. We want this to be columnar, so I'm going to say give this a new axis equals 1, and we'll go ahead and concatenate this to our pred var. So I see the error. All right. Oh, yeah. So what I want to do is I want to go ahead and have these things all in one sort of parentheses internally, and then I'll go ahead and do that. So it's still not like a new axis equals 1. Let me check that out real quick. Okay, just checked real quick, and it looks like what our issue was is you don't have to say equals 1. You just say I want this on the new axis. Oh, what am I missing? np.new axis. There we go. And it's the same old story. All right, so now we can look at our matrix here, and we can see a column of ones followed by the columns of the variables that we included for our prediction. So that is all good. So now we're really ready to start thinking about what kind of constraints you want to have on our quote-unquote regression. In this case, I'm going to want to assume that we want everything to be above 0. And I'm also going to want to assume that we don't have too many max constraints. So regardless, let me just go ahead and run through these right now. So what I'm going to do is I'm going to go ahead and just create these vectors constraints. And I think for simplicity's sake, I think that's fine for our example. I think if you had a real working system, you'd probably want them all first declared as separate variables. But I'm just going to go ahead and call these maxcon for max constraints. And I'm just going to declare it as a vector. And I'm going to go with, for maxes, we'll just go super, super high. And higher than we think the actual variables are going to get to. The actual coefficients we'll get to. And that'll just kind of work as our infinite constraints. And so keep in mind, we also, since NumPy and LSQ linear especially doesn't know that we're really trying to make a regression, it thinks the ones are the same as any other variable. So the first set of constraints we're giving this are for that fixed cost coefficient. So those will be constrainable as well. So min-con is where this gets interesting. I'm thinking we don't care if we have zero fixed cost in our model. We'll see what that looks like. So, but we're just going to use it for explanatory purposes. And also, so what was next? So the lot area, I'm also going to put 0, and I think the living GR area is also going to be 0. But, I mentioned $10,000 earlier times each number of cars in the garage. I think you can make a case that you'd want it to be somewhat substantial. So I'm going to go ahead and because it's such a small number, right, you're only going to have cars in the garage from like 1, 2 to 3 to 4. And so I'm just going to go ahead and put 10,000 as our minimum constraint. So we've done really two things here. It doesn't look like much, but we've made sure that the regression is going to stay above 0. And that's really important, and that's not something you can guarantee with a regular regression. And now we've gone ahead and constrained an extra variable to be above 10,000. So that's also helpful as well. And by the way, this is all related to this discipline called hedonic pricing. And if you're interested in sort of this method and structure of pricing things, then check out hedonic pricing for more information. All right, so I'm just going to go ahead and toss these into arrays so that we can begin to put them into the final function. So I'm going to call this maxr because I'll use the convention I used earlier, and I'm just going to do a NumPy array. And I'll do the same thing with this min array. Okay, so now we're ready to go ahead and put this in the final results. I'm going to call this results. So I'm going to call my LSQ linear function, and first I'll go ahead and give it my independent variables, which was, I believe I called pred_mat for pred matrix. And then I'll give it my sort of target cost variable, and that'll be pred_var. I'm going to do bounds equals, give it the minimum bounds first and then the maximum bounds. And then there's this additional variable as well. If you want to know what that is, just go to the SciPy documentation. Oh, and we're going to get a little error. All right, bounds have the wrong shape. So bounds seem right. They're 4 by 1 arrays. Let's see if I can see anything else. Okay, so here it is right here. Here's my pred_mat, which is my pred matrix. I meant to create, and I should have caught this and I printed it out. I meant to create a whole new variable here with pred matrix, in fact, not with pred_var. So the pred_var was my target variable. I wanted that whole thing. Let's print this out. There we go. So now I've got a big column of 1 smashed on top of some other columns. Let's just do that again just to make sure. Yeah, one thing I don't like about NumPy is you can't print out, like a head function as well. At least you can't do it the normal way. Can't print out a shape function either, like you can with pandas. That's a little depressing, but let's see if that fixed it right there. Okay, perfect. So now we have our results, and we should print these out and just see what our final coefficients are. Let's clean that up a little bit. All right, so we can see we got basically a near zero on that fixed cost. We got a near zero. Oh man, that's going to be a horrible predictor. We got a near zero on everything except for our 10,000 for our predictive sort of variable for garage doors. So clearly a very, very bad strategy. If you were an analyst, you'd want to spend some time reworking all of those. But as you can see, it's not that hard to set up your own constrained regression. It's definitely, I think, a lot of fun to play around with optimization and see how pulling one lever changes something over there. And hopefully this has been interesting. Hopefully it might be helpful for you. And if not, maybe the next one will be. All right, take care.